Yeah, so welcome everyone to this DSI machine learning seminar. Our speaker today is Benjamin Nachman. Welcome, Benjamin. So Benjamin received his PhD in physics with a minor in statistics from Stanford University, and then after that moved to LBNL as first as a Chamberlain Fellow and now as a staff scientist. And he is leading the machine learning for fundamental physics group in the physics division there. So Benjamin will tell us today about the rise of the data physicist. So, welcome, Benjamin. I think you can get started.
Great. Thanks so much for the introduction and for the opportunity to be here virtually. Sorry I can't be there in person. So let me dive into it. And the first thing I have to do is explain this title, which is very hard to pronounce. So let me get right into it. So what is this crazy title? Because I understand that the audience is pretty broad or has the potential to be broad, I'll kind of start from the beginning. So this Phystatistics or Phystat is to the physical sciences like biostatistics is to the life sciences. Biostatistics, of course, has a long history, and the idea is that there are unique challenges from biology and medical and medicine that require dedicated statistical tools, data science tools, and that's true for physical sciences as well. And one, although not the only, but key defining feature of the physical sciences is that inference proceeds via ab initio simulation. So we have first principles models of the systems we're trying to study in many cases. Now, the simulation that we use often to encode these models defines a likelihood implicitly, and it's usually specified at the level of a computer program. And so a lot of work in Phystat and the data science machine learning aspects of Phystat is the development of algorithms for what people sometimes call simulation-based inference. So the combination of simulation with data and, as I'll say in a little bit, also scaffolded with machine learning. Okay, so let me say a little about where simulation-based inference is today, or for most of the last decades. So there's nature. We want to learn something about nature. To probe nature, we build experiments. For example, we might build a collider experiment like the Large Hadron Collider at CERN, but there are other experiments, many others. And we have instruments to examine the outcome of that experiment. And then we try to make sense of the sensor signals that are coming out of our detectors. So we try to reconstruct what it was that happened in the experiment or produced in nature. And then we have, this is like the data, real data workflow. And then we have a parallel track in simulation. So we have a theory we try to learn something about that's supposed to be our theory of nature. It has some parameters theta. And from that theory, we can make some predictions. For example, we can simulate what an experiment might look like. So for example, we can compute cross sections. We can say, imagine I'm going to collide two protons, for example, like the Large Hadron Collider. I can smash them together and I can simulate like what would happen at the level of particles coming in, particles going out. Then we can have an emulation of a detector, basically propagate those simulated particles through a simulated detector as if it were the actual real detector. And then the outcome of that simulation is basically the same as the outcome of the real detector, and we can run the same algorithms to try to make sense of the collision debris and therefore reconstruct the actual particles that were being produced. Now, this is all in the context of particle physics, where you have this exact same workflow is basically true in all particle physics. In other areas of the physical sciences, there are details that are a bit different. Maybe the simulations are not stochastic, and maybe there's time series is important or other things like that. But ultimately, a lot of the same structure is very similar. And the goal then, once we have these two parallel workflows, is to compare them. And we want to be able to compare the outcome of these two chains and then to infer something about data. And the way we've been doing that basically for all of time until recently is through summary statistics. And that's because the outcome of these reconstruction algorithms are very high dimensional. So for instance, the Large Hadron Collider, you might produce hundreds or thousands or even tens of thousands of particles. Each of those particles have lots of properties. They might hit a detector. The detector could have millions, tens of millions, or hundreds of millions of sensors, which is then reconstructed back to the level of thousands or tens of thousands of particles. And so this is really high dimensional space that we're trying to compare, and it was intractable, basically, to do that comparison classically. And so we reduce that dimensionality of that full space down to usually, say, 1 or 2 dimensions. And then from that, we can make, say, a histogram of the data, a histogram from the simulation, and we can compare them. And the idea is that we can run the simulation with various parameters, different values of theta. For each theta, we basically emulate what the world would have looked like if that theta were true. We can get a simulated histogram, and we can compare which one of these histograms looks like the data. In all three of these pictures, the data are the same, and the simulation is changing. So we can make whatever your favorite metric of closeness is, say chi-squared in this case, between these two histograms, and the chi-square we minimized at some value, and we declare like that is the fitted value. Okay, so that's like the paradigm we have right now. The challenge that is going to be the motivation for the rest of this presentation is that a lot of information is being tossed. Basically, we have these handcrafted, low-dimensional summary statistics, and they fundamentally limit the utility of these complex data. So there's a lot of information in the data that we just basically toss. And in some cases, it's not we've been doing a huge disservice to the data because the handcrafted summaries are very close to sufficient statistics. But in most cases, that's just not the case, and we're really leaving a lot on the table. And we need new tools to be able to make this comparison between data and simulation in their natural high dimensionality. So that is where machine learning comes in. So with machine learning, we can directly compare the data and the simulation at the level of the reconstructed particles, for instance, in collider physics, or at the level of individual galaxies in cosmology, or whatever the kind of the basic unit of reconstructed objects are, without having to do any data compression. So this is just enabling science that was just unthinkable before, say, 5 or 10 years ago. And it's rapidly developing. And so I want to give you a sense in the rest of this presentation for the kinds of things that we can do now in this framework that were just completely unthinkable before. All right, so that's the setup. And I'm going to characterize...
A quick question. So why only compare the reconstruction result? Why you don't compare the intermediate data also?
Yeah, that's a great question. The reason is because that step, going from, say, the sensor outputs to the reconstructed outputs, is more or less lossless. So, for instance, in collider physics, you might have a particle that goes through a detector, and it might register with, say, 100 or 1,000 detector elements. But we know that once you specify the properties of the particle, that the probability density of the whole detector just factorizes into the product over all the ones for all the particles. It's not 100% true, and for sure, it's very interesting to think about doing analysis one step earlier in the chain. But for a large part of what we care about, this one compression step, going from, say, tens or hundreds of millions down to, say, thousands or tens of thousands is actually pretty lossless. But you could imagine doing that also, yeah.
Okay.
All right. Okay, so I'm going to characterize machine learning based, simulation based inference in sort of three levels. So the first level is to compare the data in the simulation in the data space. This is sort of how I set up the problem. We have the forward model going from the theory to the data, and we have our actual experiment, and we have at the end what we observe, and we want to compare them in that space. So I'm going to start with that one. This one is the most straightforward to explain, but it has some drawbacks, which is that you need to actually have the full right-hand side before you do any inference. In some cases, you don't have the full right-hand side, and so you'd like to do inference at a different step. So, for example, let's say you want to do inference at the level of what the data would look like before there was any detector involved at all. So let's say you want to remove distortions from a detector. We obviously can't observe that, but we can correct our data by deconvolving the detector effects, and then those data can be analyzed without having a simulation of the detector, for example, or having access to the data after the detector, for example. And so I'll talk a little bit about how that is now being enabled with machine learning. And the last thing we'll talk about is what if you don't want to have any simulations at all, and we want to do inference at the level of anomaly detection without reference to simulations, because I don't know ahead of time what theory I want to probe. And that's sort of not simulation-based at all, but is relevant and a nice complement to these other strategies. Okay, so I'm going to have basically these three parts of my talk, basically depending on where the inference happens. And kind of the foundation of all these different strategies are what kind of defines physical sciences and science in particular. We require that the algorithms that we are dealing with produce uncertainty estimates. So in a sense, we don't care about point estimates at all, which distinguishes us from much of machine learning. We really only care about confidence intervals or posteriors if you're a Bayesian. But we also would like our tools to tell us something about what's going on physically, and we can improve the performance of various tasks by injecting some information about the physical systems, like symmetries and other prior information. Okay, I'm going to start with data space inference. So let me just kind of get right down to it. We would like to do something like maximize the likelihood of our data. So X are the data, X might be high dimensional, and it might have a large number of events, or say many stars, or whatever the data format is, but X are the data, theta are the parameters. Theta could be many parameters. I'm going to stick to a frequentist interpretation of everything here, because as a collider physicist, I'm a card-carrying frequentist, but I think there's an exactly analog of everything I'm going to say if you're a Bayesian. So with that out of the way, this is what we want to do, but we don't know P. Okay, so as I kind of said at the very beginning of this presentation, we have the ability often to simulate X given theta, to sample from P of X given theta, but I often don't know P explicitly. It's only encoded implicitly in the simulation, and these simulations can be very complicated. So, millions of lines of code that specify the exact properties of our forward model. And so it's just not possible to write down P of X given theta. But I still want to do maximum likelihood. And it turns out that's possible. Now there are a lot of ways to do this with different tools. And more or less, you can use generative models or discriminative models. And I could talk about generative models, but right now I'm going to focus on discriminative models. But we do a bit of both, and definitely there are pros and cons of each strategy. Okay, so one way of getting around this problem is to use a surrogate model to approximate the likelihood, and in particular to approximate the likelihood ratio. So one trick is, instead of trying to approximate P of X given theta, we can learn the ratio of P of X given theta to P of X given theta 0 for some theta 0. And hopefully it's clear that if you maximize the ratio, you're also maximizing the numerator, because the denominator is just a constant with respect to theta. But this trick is very useful because of a simple fact, which is that if you train a classifier to distinguish two data sets, that classifier is learning a ratio of the probability densities of those two different classes, or at least something which is monotonically related to the likelihood ratio in a known way. So this is great. You can turn a problem of learning a density, which is hard, to learning a classifier, which is much easier usually. So all we need then are samples from P of X given theta and P of X given theta 0. And then if we train a classifier to distinguish those data, then I claim that that classifier can be recast as a likelihood ratio estimator. Okay, so yeah, this is the kind of the key here. We can do classification instead of density estimation. So just to kind of show, this is I think the most symbols I'll have on any slide. But if you haven't seen this fact before, I thought I would just quickly highlight it. So to the physicists in the room, this is the Euler-Lagrange equation, and to everyone else, this is just a loss functional. And if you want to take the functional derivative of, say, the binary cross entropy, so this is a continuum limit, but maybe you're used to saying, the log of the f is a neural network, say, for example, you have the log and the log of 1 minus the function. And if you optimize this function, you can show that the ratio of the classifier over 1 minus the classifier is the likelihood ratio. So this is well known. I'm not the first person to propose this by far, but this kind of trick works for basically all the loss functions, and all the usual ones are related in nice ways to the likelihood ratio. You can even engineer loss functions to be even. So instead of being this crazy combination, you could even make them directly the likelihood ratio, and that also works very well. Okay, so let me now walk through an explicit example. So for example, let's say you want to look at collider physics, say colliding electrons and positrons, and out comes some collision debris. So here's like a schematic picture of what that would look like. You collide electrons in the middle point here, and then out goes a bunch of particles. They have all these wavy lines. The different colors correspond to different particles, and there are multiple kinds of particles. So there's charged particles, and they're the lines, and then there's the neutral particles, and they correspond to these kind of blobs inside a certain kind of detector called a calorimeter. But the point is that the feature space we're trying to use are all the particles and their properties. So if you have hundreds of particles and each particle has some number of properties, like a momentum, which is 4 numbers, and then a few other numbers like electric charge, then the size of the inference task in the feature space is roughly 1,000 dimensional. Okay, so fitting a function in 1,000 dimensions is kind of hard, but we're going to train a classifier to approximate the likelihood ratio. And so the first thing we need to do is we need to train this classifier, but I don't actually just want the binary classifier, because I need to know this likelihood ratio continuous in theta, because I'm going to eventually do maximum likelihood. So I want to know for every value of theta what this ratio looks like. And so there's a trick to do that called building a parameterized classifier. And so first, we need a neural network that can accommodate the structure of our data. These data are a variable length permutation invariant set. They're variable length because of, thanks to quantum mechanics, when you collide the particles, every time you get a stochastic number of outgoing particles. And also thanks to quantum mechanics, there's no way to say which particle that came out of the collision came first. So they all come at the same time, and they're indistinguishable in the physical sense. So that means that the whatever classifier I use should be invariant under permutation, under permutations of the particle indices. And there are a number of tools that we can use for that. So for example, a really nice tool is called deep sets, which is a universal approximator for variable length permutation sets. And it has a very simple form. I can write it down in the slide, which is basically the composition of 2 neural networks. One that embeds each particle in a latent space. That's this first neural network. And then you sum over all the latent space vectors. So summing is permutation invariant, and you can have any number of elements in the sum. And then you have a second neural network that ingests the sum. And so in this way, the structure is permutation invariant and variable length. Okay, but then we need a loss function. So this is the binary cross entropy loss. Looks hopefully very familiar to anyone who's trained a neural network before. But the difference is that now we want it to be parameterized in theta. So there's a little bit of a subtlety here, which is that we're not training a classifier just to ingest x. So usually you'd say, like, I want a classifier that would take examples x from p of x given theta and p of x given theta 0. But actually what we do is we promote theta to a feature itself. So now actually the classifier gets as input x and theta as if it was just one set of features. And for the first term in the loss, that sample has theta sampled according to some starting distribution. If I were Bayesian, I would call it a prior. So you have some distribution for theta. You sample the theta values, and then for every theta, you can forward model to get to the x's. And so you have x theta pairs for every example. And then on the other side, you have a fixed theta 0. So every example is drawn with theta 0. But then you just append to all the x values a theta value that's randomly drawn from the same prior. And in this way, if you train this classifier, you can show that basically the likelihood ratio that you learn is exactly the one we care about, because theta is not discriminating, and basically it just comes along for the ride, but then allows you to get the conditional fully parametric likelihood ratio. And neural networks are very good at interpolating in high dimension. So there are various strategies for sampling theta, but in any case, in this way, the neural network basically allows us to get this parametric value. And then once we have...
Sorry, I have a question. So when you draw theta and then you draw x, so do you have to run the simulator every time?
Yeah, that's a great question. Indeed, you do. And so sometimes it can be more advantageous to have a small number of thetas and then run many values of x's for a single theta. This is the expensive part. And also you could imagine an active learning strategy here, which yeah, this is a very interesting area of research. I'd be happy to talk about that more later, but that is indeed the challenging part of this. Yeah, you have to, and this is the way I've written it here, basically you run the simulator, the forward model every time that you generate a new theta, yeah.
So in the training procedure, I guess, so every, I guess, gradient step or something, then you have to run the simulator, or like you can run the simulator offline, get enough data, and then do the training? Which strategy you are using here?
Right, the first one. So, the one where you only run the simulator once. So basically, you make a huge data set of you generate a bunch of theta values, a bunch of x given theta values, and then you fix that data set, and then you train. You could imagine something which is more efficient, which somehow knows about the training and could rerun the simulator during the training step, but we're not doing that here. So all the way when I'm thinking about this problem, I'm thinking about pre-setting up a data set.
Yeah, thank you.
And one of the reasons for that is that oftentimes it's too expensive for like one person to run the simulator, and so they're like large publicly or semi-publicly available data sets that people use for these kind of things. And in that case, you can't run it yourself.
Yeah, thanks.
All right. So then once I've done this training, I have this artifact or whatever amortized object, this likelihood ratio, parameterized likelihood ratio, and then I can use it for likelihood ratio estimation. So now you can basically fix the weights of the neural network, and then I can imagine this function now. I let theta be promoted to the thing I want to fit, and so you can do whatever you want basically to do that. I mean, the whole thing is still differentiable. So you can even so in this example that I'm showing here, basically it's a three-dimensional inference problem. So theta is three-dimensional, although I'm showing a two-dimensional slice, and x is 1,000-dimensional. And we're doing this fit where basically we've frozen the weights of the neural network, and then you promote theta to be the thing you're optimizing over, and the whole thing is still differentiable. So you can just do gradient descent by moving theta around, fixing the data. And using the actual test set now. The test set is the actual data. And this just shows that basically you can start somewhere and it gets to the right answer. So this is great because we have this differentiable surrogate model that we can use for doing inference. And because it's differentiable, you can also compute the second derivatives, which allows you to get estimates of the confidence interval if you'd like. Okay. So that's an example of how we might do this task. Now in practice, it's a bit more complicated because we don't just care about the parameters of interest. There are usually many other parameters that we don't care about. A lot of these parameters are related to the forward model itself. So aspects of the detector that we need to know to run the forward model, but we don't care about. Now there are usually many nuisance parameters, but a large number of them often you can constrain or fix ahead of time. But some of them are important to fit at the same time as the parameters of interest because they covary. So there are a number of ways to get around this. So the usual thing that people do in this context is you basically just rerun the fit by changing one of the nuisance parameters one at a time. This is how everyone has done it since the beginning of time. And even in the machine learning era, people often do. The plot I'm showing here is a one-dimensional inference problem, looking for some simulated Higgs bosons, and it's the likelihood contour. So the fitted value of mu is at the minimum, and you want this parabolic shape to be as narrow as possible. And there are different strategies that are shown here. So the baseline is in blue, which is a little bit hard to see, but it's the widest one, or it's close to the widest one, where that's kind of the ad hoc strategy. So basically the neural network, it doesn't know about the nuisance parameter. Another strategy is to construct models that are insensitive to the nuisance parameter. So there are a lot of tools. The one that's shown here says adversarial. So you could train an adversarial model, and there are other things like adversaries that allow you to construct likelihood ratios or things like them that basically don't vary if you change the nuisance parameters. So that dramatically simplifies the inference task, because then you can just forget about the nuisance parameters up to caveats that I can talk about later. But it may reduce the sensitivity. And ultimately, the best thing you can do is basically pretend the nuisance parameters are parameters of interest. Let them be just as important as the parameters of interest and parameterize on them, and then profile them out if you don't care about them later. And that's the best you can do. Basically, in this case, it's the best as if you had access to the real value of the nuisance parameter here called Z. Now that works really well, but it's not always possible because the strategy I mentioned in the previous slide, it works really well if theta is pretty low dimensional, but it does not scale well to many parameters theta. And I'm happy to talk about challenges there later, but that's kind of an interesting area of research. Okay, the last thing I'll say about this is that we have an ongoing data challenge, which I just want to quickly highlight. This was a data challenge that was at NeurIPS this last winter, and it's actually continuing for a second phase of it. But basically, with some collaborators, we noticed that a lot of machine learning, industrial machine learning, is about point estimates. And like I said earlier, we don't really care at all about point estimates. We care about uncertainties. And so we try to build this challenge where the goal is not to predict at all point estimates, but to give confidence intervals, in this case, on the same problem I was just mentioning in the previous slide, this Higgs boson cross-section. And we care about precision and accuracy, and we had to think a lot about how we would kind of trade off the two of those. But the challenge is still open, called Fair Universe. And we also have an interesting platform for other people who want to host challenges in the future. It can be used kind of as a way to run similar challenges. Okay, so that's part one of my presentation, and now I'm going to talk about inference in the latent space. So here, the idea is that we have, say, data that look like this, where not to scale at all. You have your kind of dynamics of particles on the left-hand side, and then you have interactions with the detector on the right-hand side. And all you get to observe is the right-hand side, but you want to learn something about the left-hand side. And so we have the data space, that's the detector part. And this latent space that we want to learn something about is all the particles. And it's a physical latent space in the sense that it's defined by particles and their properties. And so we'd like to go from the data space to the latent space. And traditionally, the way people did this task, this deconvolution task, in order to make the data independent of the detector, was to discretize the problem. So once again, first, project the high dimensional space into a low dimensional space, so make it observable, which is like, say, 1 or let's see 2 at most, maybe 3 at most features. Then make a histogram, and you can apply that same function at in the latent space and in the data space, and now you have 2 histograms. And if you think of the histogram bin counts as a vector, then basically you can say, okay, I just have a matrix equation. So I have my truth histogram. I have some kernel or response matrix, which encodes how transition probabilities from the truth to the measured. And then I just want to invert that matrix. And just inverting the matrix usually doesn't work very well. I mean, for one, it's not usually square, but also because the detector distortions, it usually has all sorts of artifacts by just inverting, but there's lots of regularized matrix inversion techniques that people have invented over the years. Now, I'm not here to talk about traditional methods. Instead, I want to talk about how we can use machine learning. So one thing you could do is imagine using machine learning to define observables. So in this context, the observables in the latent space have to be physical, but the observable and the detector space can be whatever you want. And you could design it to make the traditional method more efficient. But I'm also not here to talk about that either, because it still uses traditional methods. Instead, if we think big, thinking about things we could not imagine doing before, could we go directly from the data space to the latent space, just at the level of, say, individual particles, in this case, without first doing any dimensionality reduction at all? And the answer is yes. There are now a number of proposals, but the one that one of the ones my group has proposed is called omnifold. And omnifold is an EM approach. So EM is expectation maximization. So it's an iterative 2-step approach. 2-step because you got an E step and an M step. And now I'm going to just briefly introduce the algorithm. So the idea is that you have on the top row here, this is nature. So you have your observations in the top left. That's the stuff we see from the detector. And then the latent space is the top right. That's what we don't see, but we want to infer. And then the bottom row is the simulation of the process. So you have your simulated latent space and your simulated detector output. And the point is that in simulation, the bottom left and the bottom right come paired. So for every, in this case, event, I know what it looks like before and after the detector. The detector response is stochastic, so there's no one-to-one mapping, but every time I run a simulation, they come in pairs. So the first step of this algorithm is to learn a density ratio that morphs the simulation at the detector level to match the data. And I already told you earlier that we can use classifiers to do this. And so because classifiers they naturally ingest continuous data, that means they're unbinned by definition, and it's very easy to go to high dimensions because neural networks can very naturally accommodate 10, 100, 1,000, 1,000,000 dimensions, no problem, as long as you have enough training data. So that's the first step. And then we use the fact that in simulation, we have a pairing. So basically we have these importance weights, these weights we've derived in the data space, and we just pull them back to the latent space. Because for every event in the latent space in simulation, I know what event it was in the data space, so I just assign the same weight. And this induces a new spectrum in the latent space. And the reason I can't stop there is because the detector response is stochastic. Basically, every single point in the latent space will be assigned a bunch of different weights because they could be mapped to different points in the data space. And so we need a second step, which is kind of a regularization step, that basically locally averages. So for a single point in the latent space, we just take the average over all the weights. And that way, we now have a function which is a proper function of the latent space. And it turns out you can also view this as a likelihood ratio problem, where you can train a classifier to distinguish the starting simulation in the latent space from the one that's induced by pulling back the weights from the first step. And then you get a function of just the latent space itself. And you could stop there. But you can also take these weights and push them forward back to the data space, and the whole procedure can be iterated a bunch of times. And one can show that it's unbinned by construction, and one can show that if you iterate infinitely many times, it actually converges to the maximum likelihood estimator. And because it's a neural network, you can easily add more features. It can easily improve the accuracy by integrating more features. And most importantly, when you unfold everything, you can compute whatever observables you like after the measurement and not before. So basically, to give you context, it used to be that if you made a measurement of some observable, it could take, say a couple of years to make that measurement. And let's say you show it at a conference and that someone at the conference says, oh, that's great, but wouldn't it be better to do like a little bit different observable? You say, okay, I'll go do that. And you go off and you spend a couple of years and you make that measurement and you come back a few years later. So now you make one measurement, you go to the conference and the person says, oh, wouldn't it be great if you had done this instead? You say, just 1 minute, you go to your laptop, you do this for like 5 seconds and you get your new observable. So this is just like dramatically changes how science would proceed if it can be that way instead of the kind of months, years development cycle. Okay, because I have to give one example. I just picked a random one, but there are now half a dozen or so results that are coming out with this kind of technology. This is one from nuclear physics where it's a measurement from electron-proton scattering at a collider called Hera. And basically this particular measurement was designed to explore where oscillations inside the proton come from, whether there are inherent oscillations inside the proton that give rise to perturbations, or you have basically the protons radiating some particles that jiggles them around. And these two effects kind of compete. And it turns out that this multidimensional deconvolution strategy allows us to kind of explore the full high-dimensional picture of this effect. I mean, this is just a one-dimensional projection of an 8-dimensional measurement. And the x-axis here is the imbalance between the measured hadrons in the event and the scattered electron. And they're more balanced. They're not exactly, but if there's just momentum conservation, they'd be back-to-back and balanced, but because of this inherent jittering or because of this radiation, they're kind of imbalanced. And this measurement allows us to probe these two effects, which are more relevant at low and high values of the imbalance. But this measurement, which is done in 8 dimensions, would have been totally unthinkable, say even 2 or 3 years ago. Okay, and we're kind of moving forward now. So there's a lot of still interesting development required. So we want to build software tools around these, and there are many experiments which use these kind of tools. So we now have standard tools which are becoming better. But there's also other interesting questions, like how do you present a measurement where the actual result is a neural network? So how do you present it, like publish it in a standard format, but also how do you interact with it? And there are a number of interesting challenges associated with that as well. All right.
When you perform the deconvolution, do you know the kernel precisely?
Right. So yeah. So we have this. Oh, go ahead.
Go ahead.
Yeah, we have the forward model, And everything I've said so far basically assumes that the forward model simulation is correct. But in practice, no, we know it up to nuisance parameters. And that is also an interesting thing. I don't have time to talk about it, but you can basically extend this algorithm to also simultaneously fit nuisance parameters. It just makes it more complicated, but indeed it can do that.
But I suppose that you are not interested in the kernel itself.
No, well, I mean, the kernel is a necessary ingredient to do the deconvolution, but we don't care about it, right?
Okay, okay.
But it's also it's complicated. I mean, I talk about it like it's like a function I can write down, but I can't write it down. It's a really complicated thing that we only have access to by running the simulation.
Okay. Okay.
All right. Okay. So then on my whirlwind tour of these topics, I'm going to get to the last part. So simulations are great. I spent the whole presentation so far talking about them, and they're an essential part of machine learning, the physical sciences, but not the only feature. And sometimes there are good reasons to reduce our reliance on them. And one of the areas is anomaly detection. But like simulation-based inference, anomaly detection is an area where we need new tools for the physical sciences. In particular, in industry, a lot of attention goes into point anomalies. So a point anomaly is you see a data example and you know exactly right away it's an anomaly. So if you're like out walking and you see a flying pig, you say, okay, that's obviously an anomaly. But let's say you're at a farm and there are a bunch of pigs around, and the farmer says, there's actually is crazy. There's a few more pigs than usual, right in this part of the barnyard. So that requires that you know something about the distribution of pigs in the spatially in the barnyard, and that's called a group anomaly. So no one pig is weird. It's only in the context that it's strange. And basically, in a lot of areas of the physical sciences, we're kind of past the area of point anomalies. So it's only in context that things become strange. And I would say most, if not all, of the recent discoveries have been of this kind. And so it requires us to really build new tools. So one kind of anomaly detection that's pretty interesting in this context is a statistical kind of anomaly detection that I'm going to call weakly supervised anomaly detection. I didn't invent the name weakly supervised. Weakly supervised means noisy labels. And in the context of anomaly detection, what I mean is that imagine you have access to two data sets. One that is anomaly enriched and one that is anomaly depleted. B is background, S is signal. And if I could learn, and let's say the only thing that distinguishes them is the ratio of signal and background. So if I could learn a likelihood ratio between these two data sets, then I would be able to distinguish signal from background. And actually, you can show that this anomaly enriched versus anomaly depleted is actually exactly the same up to a monotonic rescaling of pure anomaly versus pure noise, signal versus background. And a special case of this, which is a really important one, is when the anomaly depleted data set is a reference. So it's just background. And so there are a lot of different strategies that people are developing for how to do this task well. Okay. Now, one special class, although it's an important example of this weakly supervised anomaly detection is resonant anomaly detection. So resonant would be there's some direction in the phase space where if the anomaly exists, it's localized. So this is generically true for, say, looking for new particles because they have a particular mass, and if you reconstruct the mass, it'll be some value. Or if you're looking to say something that's resonant in time, so a time series data, if it's transient, then it'll happen at some point in time and not other times. And basically the idea is you're looking for something like this, where there's one dimension where the signal, if it exists, is localized and the noise will be featureless. And then you can construct, say, a region where the anomaly would be, and then a region nearby where the anomaly won't be. And that gives you your reference, your anomaly depleted and your anomaly enriched samples, although both samples are basically both anomaly depleted. And then you can use all the other features that are available in the data to train these models to do anomaly detection. So, for example, one example which I'll give is the case of looking for astrophysical objects called stellar streams. So a stellar stream is a remnant. Obviously, it's a proto-galaxy that merged with the Milky Way, and the gravitational potential of the Milky Way has kind of ripped it apart. This picture on the left, you can see what these things look like. They're called streams because they look like these kind of streams of stars, and they're very interesting because they can tell us about the formation of our galaxy, but also they can tell us about the distribution of dark matter in our galaxy. So there's a good reason to look for them. And it applies in this context because all the stars in the stream are basically moving at roughly the same speed, the same proper motion, because they came from the same original protogalaxy. And so the proper motion is the resonant feature. And then there's a bunch of other properties that we can use, like where they are in the sky and the spectra of the stars in the stream, to be able to distinguish them from neighboring stars that are just part of the Milky Way. And so we can train a classifier, try to pick up automatically the presence of these streams. And this is useful because there are classical methods that can do this, but they input a lot of astrophysical modeling, which is of course good, but requires a lot of assumptions that may or may not be true. So the machine learning approach is sort of a complement to that allows us to kind of be agnostic and look for things we didn't know how to look for. So here's an example using a particular stream called GD1. And the top row is a classical method for finding, so this is a patch of the sky rotated to make it horizontal. And the stars here are the ones selected by the classical method. And basically it has a bunch of interesting features in the distribution of stars. And these features are very interesting to astronomers because they tell you about the various properties of the protogalaxy and of the distribution of dark matter. And the machine learning method is the bottom row, and it basically picks up all the same features. But there are a number of stars that are not in common between these two. And in particular, you can see the classical method is sort of like a nice bounding box. And that's because basically it is a bounding box, whereas the machine learning method doesn't know about bounding boxes or the typical size of these things. And so this is an opportunity for us. We found a bunch of stars that look like they should belong to the stream, but are not in the classical method. And now with spectroscopic follow-up, we can just check if they indeed belong there or not. And they could basically augment our ability to learn about the structure of streams, as well as to find new streams that we didn't know about before. Okay. And the last thing I'll say is that, just to kind of come back for a second to collider physics, we had this really fun data challenge a few years ago where we called it the LHC Olympics, where we made a bunch of data sets and we called them black boxes, and we injected some anomalies into them, and we said, go find the anomalies. And it was really interesting because it's hard to say like what method is best, and how to best ingest the results. But anyway, we had a bunch of different methods that were proposed. This corner plot here shows a bunch of methods. So here there are 4 methods. They have names like theta and cathode and curtains. And in this case, these plots are showing the anomaly score that was given by each of these methods and how they're correlated. And ideally, you'd like to find methods that are complementary. And so here, when there's no signal injected, they basically are relatively uncorrelated. So that's kind of good. They basically pick up different noise. But then when you inject a signal, they become more correlated and basically pick up the same anomaly, which is great. And this exercise was really very fun. The data sets are still public for those who want to play with them. And we actually had one of our black boxes had nothing in it just for fun. And it was pretty interesting to see people come up with, proposing methods that some were robust and some were less robust. But it was certainly an exciting challenge that resulted in a lot of new methods. Okay. We're trying to scale these things up and build infrastructure. There are a number of interesting challenges related to that. One thing I haven't talked about too much so far is that in all of these methods, like neural networks is a stochastic process training them. And so all the test statistics, whether it's for anomaly detection or deconvolution or for parameter estimation, they're random. And this has required a lot of regularization and ensembling, and these all lead to interesting computational challenges, which we're trying to work on now. Okay. So that brings me to the end. I've covered a lot of ground very fast. And I've talked about how we can use simulations or not to do inference coupled with machine learning. And the key here is to be able to look at the data in their high-dimensional spaces without first doing any compression, basically avoiding histograms and other low-dimensional summaries. And I hope I've convinced you that we need innovative computational tools to make the data-driven discoveries of the future. We're leaving a lot of information on the table. This is not just about improving things, although machine learning will do a bit of that too. It's really about enabling new discoveries that we just couldn't do before. And this kind of phi-stat area, the intersection of statistics and physics and machine learning, is really growing and needs contributions from a new crop of researchers who have experience and training at this intersectional area. So I think that's it. Thank you very much.
All right. Any questions? People on Zoom? There are some. Mike on Zoom.
Yeah, can I quickly ask at the very end of your first section, I forget your labels. Yeah, data. Yeah.
Maybe here or
yeah, so right, yeah. So I guess this likelihood space was somehow determined by doing a multi-dimensional comparison of data and Monte Carlo. Is that right?
Right. So the comparison is in 1,000 dimensions. It's all the full phase space. So you can think of it like, it's using all the particles and all their properties all at the same time. And there's only 3 parameters. So it's a very high dimensional feature space and a very low dimensional parameter space.
Right.
Yeah.
And
Imagine you're comparing data and simulate, Monte Carlo and data in 1,000 dimensions or something. Yeah.
Right. So what's the mechanism for that? You train some or yeah. I mean, how? So like where does the network get inserted in order to accomplish that comparison?
Right. So it's using this likelihood ratio. So that's pretty standard, right? Usually X is a histogram, and then you have a ratio of histograms or something. But what we're doing here is that we learn this thing. Basically, you have a first step where you train this parameterized classifier, and then you reinterpret it as a likelihood ratio. And then you freeze the weights of the neural network. So now you just forget that it's a neural network, and it's just a function. And then you can use it to optimize over theta. So that's why this first step, basically, you train this classifier, and the classifier ingests the full feature space, and it learns basically the likelihood ratio conditioned on theta. And that's how you get this surrogate model, or this sort of approximation to the likelihood ratio.
Okay, yeah, I have some follow-up technical questions, but I'll wait till we meet in person to ask them.
Great, yeah, happy to discuss further.
Ryan?
I had a quick question about how exactly is the generative model for this version of inference different? Is the generative version using something like a transformer architecture to upscale the data set, or how is like you mentioned the generative model, how is that different exactly?
Yeah, so the architectures are the same. I mean, you could use deep sets or a transformer or whatever here also. The difference is that, say, instead of using a classifier, you'd use something like normalizing flow or diffusion model to be able to sample from the way you'd probably do it is you'd say learn the distribution of theta given x. So you learn like some people call neural posterior estimation. And that would be a generative model. Either you do that, or you could also learn p of x given theta, and then either the numerator separately. And then once you have it conditioned on theta, you can then optimize. That's the difference.
Okay, and is that generally a worse method to use, or is it similar to? Does it have similar performance on different tasks? How is that better or worse in different ways?
Yeah, there are pros and cons. I mean, an advantage of doing it in the classifier way is that if your theta 0 is a good guess, then the classifier has an easy time. So learning a correction is often easier than learning the full thing from starting point. However, there are also advantages to using, say, a normalizing flow. Normalizing flows have certain regularized, they're inherently regularized because they integrate to one, for example. So it's basically application specific which method is better, but they're quite comparable on benchmarks where you've tried both of them.
Okay, thank you.
Brian?
Yes, hello. Thanks for a very nice talk. So I was a little curious if you, kind of especially on the subject of kind of deducing the uncertainty in your parameters of interest. If you think there's kind of any place for Bayesian methods in this case, especially since now we're kind of seeing the rise of kind of using the same technologies of variational inference and automatic differentiation in kind of probabilistic programming. Do you think there's kind of any place for that in this area?
Yeah, definitely. I mean, both in the surrogate modeling itself. So as I mentioned here, one of the biggest challenges is like, how do you learn this parametric on theta? That's true whether it's a normalizing flow or a classifier. They both have that problem. And you know, also getting the confidence intervals if you want to not just compute through, if you want to like go beyond the Fisher matrix. But then there are also other pretty interesting ideas where people have just started to think about what if the simulation itself was differentiable. And there are some people have started basically making the simulations differentiable, and then that opens up a whole new area of inference also. And you can couple differential simulation with probabilistic programming, and there are some early examples of doing just that. But yeah, no, for sure, it's quite interesting.
Thank you.
Even if you're not a Bayesian, I would say.
Yes, of course, that's right.
Nadia?
Yeah, I just had a quick question about sort of in the last part on the simulation free, where you had kind of like, I guess it was galaxies, but looked like a bump hunt.
Yeah,
the one
exactly. It's a bump hunt. Yeah.
Yeah, like this one. Yeah. So since you don't know a priori what sort of proper motion bin you're looking for, so do you like do a sliding when, do you kind of slide along and you have to repeat it every time at every option still, or are there ways around doing that kind of process?
Right. We don't know where the proper motion is, so indeed you have to scan. However, you scan in one dimension, but the actual analysis is done in, say, many dimensions. In this case, it was done in 5 or 6 dimensions.
Mm-hmm.
And you don't pay a trial. The reason scanning is bad is you pay a trials factor,
Mm-hmm.
but you don't pay a trials factor from the other dimensions. If you do this like classically, you would imagine like having many bins in all the dimensions and then doing it that way, and that pays a big trials factor.
Yeah. Okay. Yeah, that makes sense. Yeah, thanks.
So I have a follow-up question about anomaly detection here. So when you use machine learning tools to do anomaly detection, are you typically treating it as a classification problem, or is it something that's more, anomaly detection? Basically, what kind of tools are you guys using for anomaly detection?
Yeah, so I would say the classification version is anomaly detection. And yeah, so I was very fast about it, but basically tools that people often think about for anomaly detection, like autoencoders or things like that, those are more well equipped to find point anomalies, things that are basically impossible under the noise only hypothesis. But if you're looking for things that are not impossible, they're just, a bit more likely or a bit less likely, then you need tools that are good at, like, say, density estimation or density ratio estimation to do a hypothesis test. And there, a lot of the challenge actually doesn't go into the classifier itself, although there's a lot of work on that aspect, but a lot of work goes into how do you get the reference. So how can you infer from the data a reference that you can then use to compare with the actual data? And so it's just a different kind of anomaly detection than looking for point anomalies.
So yeah, because people are using this term in very different ways. So I suppose when you say the density estimation, you are estimating the density for the non-anomaly points, right?
Right. Yeah. So a lot of work goes into estimating the density of the non-anomaly points. That's right. The reference sample.
Okay.
Yeah. I mean, it's anomaly detection in the sense that I don't know what I'm looking for. So it's still anomaly detection in the usual sense. It's just different kinds of anomalies, and you need kind of totally different strategies to find them.
Yeah. Okay. Any last? Yeah, Tim.
Okay, so thanks for the talk. So I have one question regarding the reconstruction. So sorry, I'm not a physics expert. So I'm wondering in those kind of tasks, let's see, our output are high dimensional, and maybe we have different like physical features, and those features may have different units, right? Those different units may have different magnitude. So in this case, we consider about the reconstruction. So how do you do the reconstruction loss? For example, like if you measure the length of object, you can use meter. like millimeter, right? This kind of thing. And then if you are like measure, let's see the energy of this object, you can use like different magnitude of those units, right? But when we calculate the reconstruction, then if we use like the normal, like 2 norm laws, then actually there is a magnitude issue. I'm thinking about this problem. So if you want to use this to infer the parameters that govern this system, right? Maybe like a little difference in the loss function going to give you different reconstruction error, and then assume we cannot achieve like 100% accurate reconstruct because of noise or whatever other things. Then in this case, the parameters we inferred in this case might be very different. So how to deal with this problem, or is this really a real scenario in your application?
Yeah, thank you. And you definitely don't have to apologize for not being a physicist. Yeah, absolutely. I didn't talk about it at all, but the reconstruction is indeed not, it can become better and worse. And the better it is, the better the downstream inference task is. And you're absolutely right that, if you do this as a regression task, then you have to decide how you're going to do it. And, there are different magnitudes involved for exactly the reason you said. So this is indeed an interesting question. And there are a number of interesting, solutions to that problem. I mean, it sounds like you have also some interesting solutions. One that we thought a bit about is, embedding the data into a latent space where you can kind of just remove all those problems, or turn the problem into a classification problem where the changes of units just cancel out in likelihood ratios. But yeah, it's definitely relevant.
Thank you. Yeah, thanks.
All right. Any last question before we close? All right, let's thank the speaker again.
Thanks again.
Yes, thank you guys.